Well, good morning, YouTubes. Um, was going to talk about measurement systems and point out why they're not broken, yet it's easy to say they're broken. But it turns out it's complicated, and I need some presentation ability to be able to go through it. And by then I'm writing a paper and something else you can really find better presented through better educated individuals. So, but just a quick speak to measurement systems and what you're measuring. The first thing is to understand what you're measuring. So I'm going to play with strictly length measurements, right? Now, length is measured in inches or millimeters or miles or light years. So length measurement gets complicated, right? Now let's go specifically into the metric system. And I'm doing this from memory because I left my notes downstairs. And I should have a computer open to keep references straight here. So pardon any confusion that I add to you, but I think you were confused when you came in the door. Most people don't listen past 2 or 3 minutes of these, so we'll see how long this one lasts, what it's worth. All right, so measuring length. I get a tape measure out. Tape measure can have inches or meters or fractions of meter, like millimeters, micrometers, decimeters, whichever way you want to go. So I'm going to talk about the metric unit of measure of length, and specifically the measurements begin with meters. A meter is a full unit of length in the metric system. In the US SAE system, or the 3 or 5 other names you can call our measurement system, uses inches. But let's go stick with millimeters, because I can do the same thing with the inch measurement, right? 12 inches in a foot, 3 feet in a yard. Basically, a meter is a yard, 3 feet. Very roughly. It's a good number to keep in mind. Another number out there, measure of volume, is gallons and liters, right? So you're measuring volume, you're just using a different scale, different measurement system to say how much volume you have. I get gallons. Gallon weighs about 8 pounds, just as a very rough number, depending on what it's a gallon of. But liquid, we're going to use 8 pounds, let's say. Water, the weight of 1 gallon of water. So we measure things. Basically, we measure things. Metric system. We've got meters, right? 1 meter, about 3 feet. Then you've got tenths of a meter, right? 0.1 meter is 1/10. You've got hundredths of a meter, 0.01 meters, or 1 centimeter. Cent is 2 decimal places. Then you have a milliliter, which is 0.001, 3 decimal places. Then you have a micrometer, is 6 zeros to the left of whatever you're measuring. So 0.000001 is 1 micrometer. Nanometer is 10 to the minus 9 zeros. 8 zeros and a 1 after the decimal place. Something few have heard of is an angstrom. An angstrom is an optical wave measurement that has kind of gone away, but an angstrom is 10 to the minus 8, no, 10 to the minus 10. So somebody could throw an angstrom measurement in there, and you would have to convert it to a millimeter measurement, or a micrometer, or a femtometer, or whatever other splits there are. So you've got some odd denotations, right? Every 3 you've got milli, micro, nano, pico, femto. Each one of those is 3 zeros, but in between you've got some odd ones, like centa. Centimeter is 1/10, 1/100th of a meter, right? 0.01, 2 decimal places. That's 1/100th of a meter. Now, all of this mentally might not be making sense. You'd have to pull out a ruler, or a tape measure with centimeters on it, or a micrometer with a finer schedule. When you get down into measuring really fine measurements, you can get into optical wavelength measurements. But these are all frequency measurements. Frequency is a measure of distance over time, and frequency is typically in seconds, unless it's denoted otherwise. So 60 cycles per second is exactly that. It's a sine wave. There's 60 sine waves that happen within 1 second. And I'm still not helping with measurements much, am I? But what I'm trying to say is it can get confused and complicated very easily. So I've gone into just measurement of length. If you have a square inch of something, that's 1 inch width and 1 inch height, you've got 1 square inch. It's now a volume or an area measurement. So if you own 1 square inch of land, that's what you own. 1 inch by 1 inch of the dirt that you're looking at. Somewhere in a title or a deed elsewhere says whether you own the air above it and the soil beneath that. So these measurements turns into rules, turns into your lot line, and turns into linear feet in a square into square feet in your plot. Now, again, I wish I could present this well, because the next step is taking some of these other measurements, high energy measurements. These are subatomic particle measures, right? These are not measurements of electrons or molecules or elements. They're measurements of components of elements and isotopes. So the energies we're measuring are very unique. They're not electrical. They're high energy, high frequency energies that have effects across the biological spectrum. And we are starting to understand those effects. This gets into measurements. I'm going to speak next. I went from a meter to a millimeter, a meter to a centimeter to a millimeter, right? 0.0, 0.000, micro, milli is 3s, micro is 2, milli is 3. That's micro with an M. And then there's micro with a small u, which is 6 zeros. Milli, micro, nano is 9 zeros, pico is 12 zeros, femto is 15 zeros, and we're out into 23 to 25 zeros when we're doing measurements at the LIGO level, at the gravitational wave measurement level. So that is using distance to measure gravity. It's using interferometry in a very specific application to measure gravity. That is a whole nother video and 6 months of physics to draw into. And I know about 3 months of it. Good luck. So measurements. Let's get into radiation measurements. And here I'm going to mess up a bit because I'm going from memory and not notes. But in radiation measurement, you have Roentgens, you have electron volts, you have frequency measurements, you have high energy particle measurements of a multitude of particles. This is CERN's land, right? CERN is measuring particles released from subatomic actions. Those particles are muons, leptons, electrons are in there because they get tossed in this. Gamma rays, alpha rays, beta rays, neutrons. There are how many components inside of the nucleus of an element that have interactions depending on the size and the number of particles inside the nucleus. Now you're beginning to talk a little bit about how the sun works and why the Parker Solar Probe is telling us something. So, measurements, Roentgens, counts per minute, counts per second, sieverts. This can be done with film, measuring the dots and counts on film, and that is film, I forget the scientific name for it, but all of these techniques are being applied. You can find folks in Fukushima that are using photographic film to measure radiation levels. And if you research into photographic film, you'll learn that Eastman Kodak helped to build. All these film manufacturers helped to build some of the detectors, some of the initial detectors, like film. Once we learned film could detect radiation very easily. Long lesson, 50, 60 years old, goes back to atomic testing and actual film contaminated from being near the nuclear test sites. Someone got curious, and even Madame Curie used film. There's other techniques, gas chambers, where you can see ions moving particles through a gas chamber. Lots of videos about how to make those things. Very few teach you exactly how deep the science is behind those things. Radiation detectors, gamma detectors, scintillation crystals. There's now diodes. That's kind of the latest trend, is these CCD devices, basically very sophisticated, expensive cameras that can see radiation energy, just like we see infrared energy, and that technology is about 3 to 5 decades old. It's just not publicly available till recently. Now you can go buy a FLIR heat camera to check your electrical cabinets for overheating. You can go buy a FLIR camera that can measure CO2 releases and look off in the distance at a chemical factory and give you some ideas what's coming out of the stacks. We've got another high energy detector that's actually using optical emissions to be able to measure the elemental and isotopic abundance of what's in a rock. That used to be a lab that you sent the rock off to somewhere and got results back 6 months or 2 years later. Now it's a very expensive instrument that a researcher with the resources can take out and point at a rock, point at something. Okay, this is interferometry. Interferometry. So, and some high energy particle physics going on. These are measurements that are so cool. So few understand them. That's why I'm here, folks. Not to teach you, to get you curious and go learn. Alright, so we're at 15 minutes now. This video won't be watched more than 3 minutes according to my averages, and not that it matters anyway. But the idea is to let people know what we do in the real world. What those sneakers that go back into the labs take with them and learn. What those towers of knowledge have stored inside of them that most folks aren't aware of. You weren't invited, you walked past the door, you weren't invited in, or you're even kept out. So these are the vagaries of our life today. How do you get folks interested in these measurements and understanding them, and how discrete, precise, and accurate they are? Then, once you have the measurements, you can start to say, what does this mean? So we have a right to these numbers. I just dabbled. It Geiger counter, size, different types of readings and these instruments, and they cross over. One thing can do another if you understand how to subtract the noise that one thing is seeing. So, alright, this one's way too long again. Peace out, brothers and sisters. Teach your children. Didn't work for me, but still good advice. Love you.